Hi guys, and welcome back to Clinical Neurology 101, and my name hasn't changed since the last time we spoke, so I'm still Shane. And today we're going to be talking about the frontal lobe, or as it's known in Latin, the lobus frontalis, or whatever that says. So, the frontal lobe is actually responsible for a lot of our voluntary conscious movements. It's responsible for our conscious motor movements, and even our involuntary motor movements. And it also plays a big role, as you can see over here where I've outlined our executive function. So any planning, decision making, and conscious cognitive processes, those are typically going to be mediated by the frontal lobe. So up here we have a diagram just showcasing the actual frontal lobe as it relates to being part of a cerebral hemisphere. So when you look at the lobes of the brain, they're actually divided up in the cerebral hemisphere is actually divided up into two hemispheres, the right and the left. So if you had the other side here, that would be the cerebrum, and each lobe of the brain is present in both sides of the cerebrum. So for this one here, we have the frontal lobe of the left cerebral hemisphere, if we're looking at this from a patient's perspective, and if you're seeing this coming this way, so this would be the medulla oblongata, this is the cerebellum, the corpus callosum, the hippocampus, things like that. This is going to be in the middle, this is going to be the right, and this is going to be the left. So when we're actually looking at a diagram of the brain and you're seeing a hemisphere and you're seeing an actual lobe like this, for example, it is present on both sides. So this is kind of what this diagram aims to show you. So if we're looking at a front facing, this is going to be the frontal lobe. So the frontal lobe is separated from the other lobes of the brain by the lateral sulcus or the Sylvian fissure and the central sulcus. And the central sulcus comes down here and separates it from the parietal lobe, and the lateral sulcus comes up here like this and separates it from the temporal lobe. And the lateral sulcus is also known as the Sylvian fissure, named by Francesco Sylvian for being one of the first people to actually portray the brain as having this line that separates the frontal lobe from the other areas of the brain. So, just to have that kind of anatomy out there for you, we're now going to go and actually discuss the frontal lobe in detail. So, first up, we have the motor cortex, which is comprised of the premotor, motor, and then on top of that, we have the prefrontal cortex, which is responsible for a lot of our decision making and planning. So for the motor cortex, we have the primary motor cortex, which is responsible for generating neural impulses. So the actual impulse from our brain to move our hand, that comes from the primary motor cortex. Then we have the premotor cortex, which is responsible for a lot of our preparation and sensory and spatial guidance of movements. We have the supplementary motor area, which is responsible for motor planning. And we have the posterior parietal cortex, which is responsible for transforming sensory input into motor input. And finally we have area 3A, which is responsible for our motor control. So over here I've actually outlined all of this, and you can see all of that up there is the motor cortex. I've outlined all of this here. So here is our supplementary motor area, and this is taken out of a cross section from this part of the brain. This is the premotor cortex. Primary motor cortex is down here like that, and then over here we have from the parietal lobe, we have the primary somatosensory cortex here and the posterior parietal cortex here. So the somatosensory, again, that's body sensory, somato is body. So that's that part. And down here I've just taken an aside to show you the Broca's area and introduce you to the concept of having a dominant hemisphere, as well as introducing Brodmann's area. So Corbinian Brodmann was a German neurologist who was responsible for dividing our parts of our brain into Brodmann's areas, the cerebral hemisphere. So in this area we have here Brodmann's area 45, Brodmann's area 44, those comprise the Broca's area. And the Broca's area is located in the dominant hemisphere, the frontal lobe of the dominant hemisphere. So If you're left-handed, you have a 60% chance of having it in the left cerebral hemisphere. If you're right-handed, you usually have a 100% chance of having it in the left hemisphere. If you're left-handed, you have a smaller chance of having it in the right hemisphere. So the Broca's area is in the dominant hemisphere. It's responsible for linguistic processing and speech production, and usually when the Broca's area has a lesion in it, it results in Broca's aphasia, which is a breakdown of the ability to produce speech in a fluent manner. So usually people with Broca's aphasia can understand what's being said to them, they just can't actually produce proper speech in response. A good example of somebody who may have Broca's aphasia is Tano Tano Man, if you've ever heard of him, where he can only count fluently, and every time he tries to say anything else, his brain reverts back to saying Tano Tano Tano, even though he understands what's being spoken to him. If you ask him a question, it's clear that he understands. If you ask him to count, he'll start counting. He understands what's being said to him, but he can't produce intelligible language, and that's might be a result of a lesion to the Broca's area. I'm not quite certain his particular medical history. There could be a lesion in many other places. It could be a result of dementia or Korsakoff's or anything like that. So that's just an introduction to the Broca's area. And that, again, it's right there, and it's usually the left hemisphere. And finally, for decision-making and planning, we have our executive function block, which is right here. So the prefrontal area of our frontal lobe, or over here we can divide it like that, this particular area is further broken down into the dorsolateral prefrontal cortex, the orbitofrontal prefrontal cortex, and the anterior cingulate cortex, which actually, if you imagine the corpus callosum is right here, kind of bridges like a collar right around the corpus callosum. The orbitofrontal is below and the dorsolateral is above. So, and this would be the rest of the frontal cortex. So, the dorsolateral prefrontal cortex, or DLPFC, is usually, I'm just going to kind of read through here, responsible for verbal and design fluency, shift set, which means our attention, our ability to actually track and maintain attention, inhibition control, so impulse control. If you see someone and you just want to say, hey, you know, you're awful, I don't want to deal with you anymore. You know, usually the social appropriateness of that will result in us, you know, kind of limiting our responses like that. It's responsible for why I didn't actually swear in the middle of my teaching video. So I'm using my dorsolateral prefrontal cortex right there. So it's also responsible in logical reasoning, working memory, abstract thinking, and problem solving. So if you're looking at like a logical syllogism, you're usually, it's going to be testing your dorsolateral prefrontal cortex. Oh, tongue twister, try saying that 5 times fast. And down below that, again, our little collar, the ACC right here. So that was this part. So down here we have our ACC. That is usually responsible for our anticipation of reward. So usually when we talk about reward, we're talking about the similar pathways that might be used when we're discussing things like addiction. So if you have someone who is addicted to a drug, they're going to be anticipating a reward from using that drug. So someone who is an addict has an overabundance of reward anticipatory neurons firing off when they realize that they're going to get this over and over and over and over and over and over and over again. And that's usually why we start to build up a tolerance to drugs, because eventually the pathways that fire and the dopamine that's released, it's no longer considered a novelty to our brain, so our brain acclimatizes to it, and then we don't consider it a reward anymore because it's not novel. So that's just a little bit on reward there. The ACC is also responsible for assisting us in our decision making. It's useful to help with empathy, impulse control, emotion, and rational cognition. So our social appropriateness, things like that, that's going to be more or less regulated by these here. Interestingly enough, it's also, sorry about that. It is also very, very highly involved in our ability to correct for errors. So if we're going to look at something like the Erickson flanker, which is this here, you can see here that there are 3 arrows that go this way and there are 4 arrows that go this way. So obviously this would be considered non-compatible. They're not even. But if I drew another arrow there, that would be considered even. So that would be an error correction process. Now, people who have any damage to their prefrontal lobe may have difficulty understanding that this is not compatible. It's just not functional. It doesn't match, it doesn't fit. And we also have here where we have the word blue written in green. So if I ask you what color is that, you might say blue, even though your ACC might go, wait a minute, that's actually green, because it's green. The actual color is green. So that error correction, that is the ACC. And we also have the orbitofrontal cortex, or this part right here. And that is, once again, helps us with our impulse, our set maintenance, our ability to maintain our attention. It is responsible for our behavioral monitoring, once again, reward and social appropriateness. So behavioral monitoring is, again, our ability to understand that the behavior that we're exhibiting may not be in line with social norms. So that's actually our segment on the frontal lobe for today. And as an aside, I have here just the map of the body and human brain. If you want to check it out on Elliatomy, it's a cool little diagram that I'm posting along with this lecture that just goes to show how our brain actually maps out the different parts of our body in the motor cortex. All right, thank you very much for listening. Have a great day.